Okay, so let's go over problem 2. Let me share this with you. Can everyone see the PDF?
Yes.
Okay, that's good.
Zoom in a little bit.
Yeah, let's see. Okay, so problem floating point numbers, comparing floating point numbers. They want us to create a function. Oh, sorry about that. A function called my compare, and the function will have two inputs, x and y. Both of them will be singular numbers, scalars, and it will have two outputs, comparison and tolerance. Comparison will be a 2x1 cell. This is a comparison of floating point values of x and y using the formula given below. Tolerance will be a single number. It will be a tolerance at which x and y are equal. So the problem says, given that two double variables x and y, compare their floating point values and determine at what tolerance their values could be considered equal to the nearest order of magnitude. This value is the smallest power of 10, such that x is within plus or minus that tolerance of y. If x and y have equal floating point values, tolerance should return 0. And there is an example below. So they have x equal to 0.3, y equal also to 0.3, but after arriving to it through the summation of 0.1 and 0.2, the function will compare those two numbers, and it will give, so the comparison will be a 2x1 cell with this format, and the tolerance will be the order of magnitude within which both numbers are the same. So this is a problem that deals with the fact that computers work in binary. So they have a limited amount of memory with which to represent numbers, and that means that a computer represents a number as a summation of powers of 2, but it is not an infinite summation because they don't have infinite memory, so it can just get to certain precision. So when you ask the computer to represent the number 0.3, it rounds it to the nearest power of 2, or to the nearest summation of powers of 2 that can get to 0.3. Within the memory usage of the computer, or the precision, the double precision. And it does the same with 0.1 and 0.2. It approximates them as close as it can with multiples of, with powers of 2. But that means that the approximation that you have, oh, what, this is not annotating. Just a second. Where's my annotation tool? Just 1 second. There you go. So that means that whatever binary approximation the computer gives to 0.1 plus the binary approximation to 0.2 may not be equal to the approximation of 0.3. And this is the case. The computer approximates the 0.3 directly as almost 0.3, which is this what you see here, and it approximates 0.1 and 0.2 in such a way that they add up to almost 0.3, but not quite. Okay. I hope everyone's okay with this concept. If anyone has any questions, please stop me. Let me get rid of this
So
tool.
I'm just a little confused as to why this is. Why is it because, like, when we have the the unsigned, what's it called? I'm sorry, I can't think of the word.
It's okay. It's okay.
When we have decimals, like point decimals, not integers, we need that. Sorry.
No, it's okay. Try to formulate your question, even though if you don't know the technical term for something, try to describe it. Or
like when 0 is like -1, or the first position in the binary is like 0 or 1, and that shows if it's positive or negative, and then there's like the amount that's raised to f and all that stuff. Do you know what I'm talking about? Maybe.
Is the question like why there's like this discrepancy between the two numbers in the floating point?
Yeah, is it because of that that equation?
Yeah, basically the reason why this is because computers store stuff in base 2, not base 10. So like if you'll have like a bunch of like what you're talking about is that like IEE, I don't know what it's called, like, but like it's basically a bunch of series of like powers of 2, and like even the decimals are like 2 to the -1, 2, 3, -30 something. And because of that, there's going to be like this like fuzziness to it, just because like you'll need like if you want to get any more precise, you'll need more powers of 2 stacked onto there. I kind of linked something in the chat. Like you can watch this on your own time. But I mean, it's computer file. It's understanding like why this is the case. And like it's also interesting when you're handling like when you're like a bank and handling money, that kind of thing, and like you need like exact numbers. It's powers of 2. That's why it's like scientific notation, but like using 2 instead of 10. That's why we're trying to work with base 10, but like you're converting from base 2 to base 10. That's kind of what we're talking about, like binary, and at the same time as like floating point numbers.
So if you think of very small numbers, or this is probably easier to understand with very, very big numbers. Oh, what was that? Oh, just a notification. When you think of very, very big numbers, so I don't know. Let's say some huge number that's I don't know.
6.
Oh, this is the yeah, like 6. No, something huge, like on the order of I don't know. As this is not the tool that I want. Just a second.
Actually, I think in this exact
here.
video, they're talking about like the speed of light, like 300 million. I'm using the metric number, but like if you're taking that and like multiplying it by like a really small number, like I don't know, Planck's constant or something like that, then you'll have to worry about like this imprecision.
And well, I'm not familiar with that particular example, but I was thinking of something on that order, something on the order of 300 million. So 2, 3, 1, 2, 3. For a computer to represent this number, this is it tries to do it with powers of 2. So you know how like 10 would be actually in the eyes of a computer, it would be equal to something like what 8 plus 2, and 11 would be equal to 8 plus 2 plus 1, and so on and so forth. Because a computer has to work on powers of 2. When you get to a number like this, this magnitude, there's a chance that this will require I don't know, the combination of let's say 20 powers of 2. And by that I mean here I'm using 2 powers of 2, and here I'm using 3 powers of 2. So probably to represent this number, I would need to use 20 powers of 2 or something like that. And a computer has just, I think it's 16 bits of memory for a single double number. And probably the computer won't be able to compute this number exactly. So it approximates it as close as it can. And oh, there's 30 million in binary. So
it's more than 16.
It's more than 16. So the computer will just try to approximate it as best as it can with the available memory that it has. But this also means that a computer will see this number and this number as exactly the same. It will not be able to tell the difference because it doesn't have enough precision to tell them apart. By the way, I don't know if this is already in the threshold where computers stop seeing the difference between one integer and the next. Maybe this is not big enough, but it starts happening. You can do this experiment in your own computers. This starts happening when numbers are big enough. If you ask MATLAB to, oh, sorry, I wanted to erase. When numbers are big enough, if you ask MATLAB to subtract 3 million and 3 million and 1, it'll probably tell you that the answer is 0. So, well, Eva, does that answer your question?
Yeah, I think so.
Okay, good. Okay, so let's go into the details of how to solve this. Let me erase this. Also, there's a tip that, okay, let me read this. To understand and visualize how MATLAB stores some floating point numbers, type sprintf of number to 5f in the command window to display the value of variable x with 25 digits after decimal b and then 0.1 place. Okay, so it basically explains the example we have below. Okay. Let me open the solution we have. Dennis, while I look for the file, I'm not sure if you wanna input something in here.
Input?
Yeah, like how to start the problem. Let me look for the correct file.
Let's see what I got.
This is a very useful command for this kind of problem. I got my files all mixed up here. I don't want to watch the video. I want to watch the, here it is. Okay. No, this is not the file that I needed.
I have it open if you want.
Oh, okay. Should I stop sharing?
Sure. If you yeah.
Okay.
So you're fine with me. So are we ready to share the solution?
Okay, yeah, let's just do that and let's go over it. I'm not sure. I have my folders mixed up here. I think
I'm pretty organized.
We're using. I should work on this. We are using the ones of fall 2020, right?
Spring 2020. Fall is like a different class.
Uh,
I can do.
okay, I'm looking at a whole different folder then.
Gotcha. Let's see. Close the tester, close complement game. Let's see. Compare floats. There we go. Okay, people can just see my MATLAB screen. Scan this out. It's not too long, it doesn't look like. Okay, wait, where's the chat? Yeah, okay, people can see it. Okay, Jose, I can give this back to you. You can still annotate, I think.
Sorry?
I can do.
Oh yeah, okay. I can annotate on that.
I don't want to like completely take the mic away from you.
Let me see. Let me move this to the right window though, because I cannot annotate on that one.
So the point 25F, that is what shows the number in 25 digits.
That's right. So the format, let me look for the right tool.
I can like do.
Okay.
Let's see what X we want to do.
Oh, here it is.
Let's 25, I guess. Oh no, let's do this first. X equals 25, and then we'll do. Whoa.
So yeah, so the format here is okay. So sprintf. This means print with format. I don't remember what the S stands for, but here the format goes the X equals something. Those are just text, and you can input special characters. The special characters that you use here are the %sign. This means some number.
F means float, I believe.
Sorry?
F means float, I believe.
Oh yeah. F means float. Percent. What did the percent mean?
That's in front of every. That's our formatting. It's just like replace.
Oh, yeah. The percent means special formatting. So yeah. So.
You can look at the documentation on that. It's like there's a whole table.
Yeah, it's a whole table, but you basically start whatever you want to replace in the. So you're telling it something like this text should be X lines long. So if you want to print something like this, but actually have a number here, you would replace this by some special formatting. You can add something like .0, for instance, if you want to this to be an integer. So this gives you the precision. Followed by the letter F. That means floating number. So when you hit enter, this would give you a sentence with an actual number that you would put in the input. So yeah, this function right here will display 25 with 0 decimals.
The one below that, I think.
Sorry?
The one below that. It needs like a decimal point. I'm not sure what this is doing.
Oh yeah. No. Yeah, you're missing the. Okay, let me clear that. So what's different between this one and this one is the decimal point. So this will display 25 as an integer. This one, I'm also not sure what it's doing. I think
Wait, let me try something.
I think that one's showing trailing zeros, something like that. There's a whole table of documentation of how to use this function, and there are a lot of things you can do with it.
I guess 0f is just the same thing as f.
Probably. But yeah, like in here, you're showing it with 4 decimals after the point, and in the example of this function of this problem, we are showing it with 25 decimals. Any ideas on why let me erase this. Any ideas of why the 25 decimal versions of 25 is also 25 and not some weird decimals after that? The reason this happens is because 25 is actually a number that you can get, that you can approximate. No, not even approximate. You can get to that number exactly with powers of 2 within the 16-bit memory constraint. So you can actually add enough powers of 2 to get to that with the 16-bit constraint. But probably if you type the 300 million example that we did before, it will give us a bunch of weird decimals.
I have a question.
Yeah, go ahead.
So, like in the case of, how 0.3 is not equal to 0.1 plus 0.2,
Mm-hmm.
and you can really only see that if it's like s print f, what you did in line 2.
Mm-hmm.
How come it can tell if x is equal to, or if x is not equal to y? Like in that situation, wouldn't x still be equal to y?
You mean if we do this test, x equal y?
No, I mean, like, I understand that if you show it in like that, it will be different. But in line 4, you just ask if x is equal to y, is equal to y.
Oh, okay,
It doesn't
okay.
ask for the sprint f, kind of thing.
Okay, so look at what this code does. Actually, yeah, we can go into this code line by line. So in the first line, comparison equals. This is only setting some text into the variable comparison, and the text will be x equals whatever number with 25 decimals of precision. This is the first text, and the second text, it will give you y equals whatever number it is with 25 decimals of precision. Yeah, so this will be comparison.
So just remember that.
Hope you excuse my handwriting. I'm writing this on my laptop, and the screen is wiggly.
Well, I mean, I guess the question is because if I were to enter in, if I were to have like a is equal to 1 plus, or 0.1 plus 0.2, and I have b equal to 3, and I have if a is equal to b, is a equal to b. And
do you think that comparison a equal to b will be true or false?
Well, I mean, based off of the s print f, it would be false, but I don't know.
That's right. So if those happen to be equal, for instance, we were doing 25 before, and we saw that up to 25 decimals, it was actually 25. That means that you can get to that number with powers of 2. I think if we use numbers like 10 and 15, I think those you can also form up with numbers of 2 within the 16-bit memory constraint. And if you add 10 and 15, that is actually 25, because those are numbers that you can get within the memory constraint with the precision of the computer. So in that case, if we were going to compare 25 to 10 plus 15, then this would probably turn out as true. and we will go into this text, and we would go into this line, into line number 5, and we would know that tolerance is 0. Tolerance 0 means that they are actually equal. But if we in turn, let me change colors here. If we in turn compare 0.1 plus 0.2 equals to 0.3, we saw in the 25 decimal representation that these are actually not equal within the computer's precision, and we would go actually into this line, to the else. Yeah. So in the else, we actually want to see the difference. That's what this line does. It takes it in absolute value because we don't care which one is bigger. And the next line, the next line calculates the order of magnitude. Okay.
Okay.
Yeah, I had only considered up to here, but
Yeah,
I
think I
hope I
get it
answered. Okay,
Yeah.
Okay.
Because every time I did like the if else, it would only compare integers rather than, point decimals.
So with small integers are you can build them with just a few powers of 2. But once you get to very big integers, I think Dennis was showing an example here, or actually
I was mostly playing around, but I think this is kind of what illustrates it. Like this is x equals 300 million.1, and then it has all of these in front of it. If you do I thought this would work, but like apparently this doesn't. Like this just has a bunch of zeros.
Oh.
But you see it with like 3 million.1, that kind of thing. Which is interesting.
So that means that 300 million is not yet big enough to not be representable within the computer space, within the binary space. I wonder how big you need to get. Huh, that's interesting. That's interesting. There is a point when the number is actually so big that the computer cannot tell the difference between it and the next number. And I think that there is a function in MATLAB called epsilon of a number that will tell you the precision around that number. That means that if epsilon of that number equals to 0.1, then that number plus 0.05 will, in the eyes of the computer, be exactly equal to the original number. So here, Dennis showed epsilon of 25. That means that within 25 plus minus that number, that tiny number, the computer will actually see the same number.
I'm gonna try this.
Yeah.
25 minus. Let's do divided by 3 actually. Actually no, divided by 2. Answer divided by 2. 1.
Yeah. So here he tested at 25 point many zeros. I don't know, 8 or something like that, and 24 point many zeros, 0.2 or something like that, and the computer actually thinks they are the same number.
So can I put numbers to these? Wait, what? Well, oh wait, I need to do like divided by. Let's do 16. Oh, that's why. I did 5 instead of 15. This should work. Yep. Isn't that weird?
And when you input numbers into that function, into epsilon, that are really big, there's a point when epsilon starts being more than 1. So I don't know, 3 trillion and 3 trillion and 1 would probably be the same for a computer.
So this next one is kind of like, let me just move this to the side if that's okay.
Yeah. And let me actually erase some of these.
So the next line is like absolute value of floor of log 10 of the difference. So there's like 3 things going on here. Wait, Jose, you want to continue?
So,
Sorry.
Actually, let me figure this one out. I hadn't looked at that line before.
So let's outline. Let me annotate too as well. So we want, so floor, by the way, is like, if we have like 5.5, that's like 5. It like rounds down. That's all that does.
Not only 5.5, but 5.9 floored is equal to 5. 5.99 floored is equal to 5. So it rounds down to the lowest nearest integer. And if you're wondering, the opposite of that is there are a few functions. Oh, I'm not annotating anymore. There's ceil of 5.5 equals 6, also 5.1, 5.01. So that's rounds up. And there's a third function called fix. That one, I think it rounds towards 0, if I'm not mistaken. Let me check real quick. Yeah, it rounds, the fix rounds down towards 0 in the sense that the difference between fix and floor would be that floor of negative 5.1 is negative 6, whereas fix of negative 5.1 equals negative 5. So those are just some useful functions for you to have in case you're not familiar. But back to the problem. Let me erase some stuff.
While you're doing that, I'll also do some stuff up here. So let's say we have a difference of like 10 to the negative 11.5, say. So we'll take the log of that. This is how we get the magnitude, like negative 11.5. We'll take the next lower number, as Jose was saying, and then that becomes 12. And then we'll take, lastly, the absolute value of that, and that becomes our n. So that's an order of magnitude of the tolerance.
Could diff be negative? Yes, diff takes, oh, this is not the right tool, sorry.
No, it can't be, because it's absolute value.
Oh, sorry, I was thinking on the function diff. Oh, that's an interesting.
Yeah, the difference for the,
This is an interesting naming for a variable because there's also a function called diff. I usually avoid naming variables the same as a pre-existing function because that can lead to some confusion. It's not necessarily wrong because in this code we are not using the function diff. So there's never any ambiguity, but I would generally avoid that. I would have gone on and named these as difference, like the whole word, or some way to distinguish it from the function diff.
Oh, also, before I forget, Jose, sorry. Someone had I think Vishal had a question for like a breakout room. Like, I'm sharing screen right now. I mean, I can like take over for you, like if you want.
Oh, sure,
sure. Thanks.
Sure. Just before I do that, does anyone have any questions on why the log 10 of the number will give us, will help us get the order of magnitude? I do. Okay. Okay. If you can go over that, Dennis. I'll go into the
Why? Wait, what was the question?
oh. Why log 10 will help us get into the order of magnitude.
Sure. Yeah, I can do that. So, so by the way, stop the recording and then I can start again.
Oh, okay, sure. Let me. This has a lot to do with how exponents work within within logarithms. Let me